All right. So again, good afternoon, everyone. This is Pauline Cantue from UAV for Africa. Welcome to our first webinar, April 2020, in the confines of social distancing and staying at home, given the pandemic. But I think it's going to be an exciting 40 minutes. Hopefully, there will be some things that you will take home. What is the plan today is quite straightforward. We will be going through some drone design and modeling tutorial. Hopefully we'll do some form of simulation that will give you perspective of what it means to design a drone, at least in a simplistic way, and ultimately try it at home. Unfortunately, the prerequisite is for you to be able to have some form of simulation software like MATLAB or Octave, but normally Octave is something that you can download for free anyway. Okay, we will get right into it. So we will be going through a tutorial which I've prepared for everyone to, and I'll make it available to everyone afterwards. So it's not really something that you have to kind of make notes. You will be able to get what is going on straight from the tutorial itself. All right, so I'm just checking if there's anybody else who is potentially coming in. All right, so let's carry on. Okay, so first things first, this is a drone development tutorial. All right, so it's in case you are in the wrong chat room, it's this is definitely all about drones and trying to get to the fundamentals of modeling first of all, but more importantly in terms of drones. All right, now when it comes to drones, it is quite important to understand that it's a very complex system. And most things that fly are quite complex in terms of modeling and simulation. And because of that, one needs to be taking the modeling effort very slowly and through a very step-by-step method. But yeah, so this tutorial is part 1 out of 3. And the main reason for that is that we will be focusing a lot on the next 30 minutes on the modeling part. There is quite a bit as well on simulation, even though we'll do a little bit. And obviously the autopilot and flight control is a tutorial on its own. So we will definitely focus on 1 out of 3 today. Okay. Just a reminder again that we will also not just make the PDF available, but we will make the MATLAB script available. You don't have to thank me yet, but at least you will be able to run the example with the tutorial on your own and obviously make adjustments as you need to. Okay, all right. So first things first, we will be simplifying the drone model. It's quite important for the sake of everyone who wants to be able to do, or at least to start modeling aerospace system. Is very important to start with the basics, and that is modeling. Okay. Getting acceptance. So very important to start with some form of simplified modeling. All right, and this is where this comes in. Now let me just try and make it slightly bigger so at least you guys can be able to see and not feel constrained. All right, so let's try again and just make sure that it's okay. Well, for some reason it doesn't. There you go. All right. Okay. So it's quite important for us to understand that a simplified version is important. I'm not going to go through it obviously line by line, obviously. So, but I think what's quite important is to understand that drone modeling is the very first step in creating new drone designs, which is one thing that's quite interesting is if you look at one of the more interesting drones out there. It's called the Black Hornet, and you will see it doesn't look like a traditional drone. It actually looks like more of a traditional helicopter, and there's a reason for that. But I'll leave you to your own devices to research why that is. But what's quite interesting is that it is only 32 grams, only 32 grams, but it can fly up to 25 minutes. Very few 32 to 50 grams commercial helicopters or quadcopters or drones, whatever you want to call it, are able to do more than 6 minutes. That's number one. Number two, what's quite interesting here is that this drone is able to do all the way up to 1.24 miles, which is roughly, I think just a kilometer and a half, if not more, in terms of range. Now, you can imagine this is a really tiny drone, and is able to do all that. And that really comes through the power of modeling. The power of modeling enables you to get to those numbers and optimize them and ultimately get to the product that you actually wish to. Okay, so I think so there is a case, enough marketing on modeling. There's a case for modeling. Now, there's a few assumptions here for those who are joining us. The assumptions here is that you are able to have access to your dynamics and statics, other lecture notes or book, because we are going to go through some maths, and we will definitely have a bit of questions later on, but definitely we will try and not dwell too much on the maths. But the important part is that, as it says here, that most things that have motion or that have some form of movement can be described in 6 degrees of freedom. And in 6 degrees of freedom, if you were to look at a picture here, a 6 degrees of freedom has quite an interesting dynamic, which is quite important to understand, but not so relevant for this tutorial. Is able to have, as the picture shows, a backward and forward, left and right, but more importantly, it's able to describe its orientation, which means how it rolls, how it yaws, as you see, and obviously how it pitches. Now, for this tutorial, we will only focus on what they call longitudinal dynamics, which means we will only look at or trying to estimate the forward and back, the up and down, and just the pitch. So there's three, and that's why it's called 3 degrees of freedom, because we're only looking at 3 dimensions. And that's quite important. But for you to go from 3 degrees of freedom and to 6 degrees of freedom, it's exactly the same process. You're just adding more complexity. Okay, so if you were to now, let's just go right into it. So if you were to now look at a typical drone, and I have a picture here, a typical drone model, and this is really, like I said, again, in a plane. So, it's in a plane, so on the paper, and how it will move. It will move only on the paper, if you know what I mean. So let's just imagine a drone with 2 motors, a controller, a battery. I've excluded everything else for the sake of simplicity. And what this drone is able to do, or at least how you quantify, you need to quantify some physical and environment properties. So things like mass, inertia, area, length, and so forth. And there's a reason for that. But more importantly, you also need to quantify the environment. The environment basically means, where is this drone flying? Is it in water? Is it in air? Is it in a vacuum? And so forth. So obviously the answer is air in this case. And there's certain things that goes with it. For example, like I said, mass, inertia. There is frontal area, and obviously the reason for it is we will calculate something called resistance or drag, and that requires an area and requires some form of coefficient of resistance, or in aerospace it's called coefficient of drag, and that allows us to be able to calculate certain forces and moments. But also quite important is this variable here. Here it's called length, but it's basically the length between a motor and the center of gravity, and that actually creates a moment. for those who remembers your dynamics and statics class. Like I said, the environment is where we set up the gravity. So the idea here is you might not have noticed, but in this tutorial, I've made sure that the MATLAB script that we will be using looks exactly the same in the PDF as in the script. So at least you're able to see where each piece of code actually lies from the tutorial and to the script, and from the script to the tutorial. At least you're able to also change variables as you get more acquainted with the tutorial. Okay. All right, so like I said, we look at the simple drawing. So what we need to do is obviously now work out a free body diagram. So most of you are engineering students, if not all of you. You have a pretty good idea of what this is. And we will try and kind of simplify it for everyone in order for everyone to understand. But basically, you are, like I said, you have, instead of a quadcopter or a normal drone, we're only going to focus on 2 motors because, you know, we fly along the plane of paper. So, you know, we don't have any depth to this drone. So there's no 3rd dimension, if I can put it like that. So we will be looking at a couple of forces on this free body diagram, which is quite important. Obviously, each drone motor produces a force, but then, like we said, there's drag, and the drag comes across due to a certain velocity. So as the drone moves through the air, it creates more drag. The less it moves through the air, it creates less drag. But the variation of the forces also creates a moment about this point, which is called the center of gravity. And that center of gravity, like obviously, has gravity acting on it, and the force due to gravity is just the gravity times its mass. What this means is, and we will look at it a bit later, is just it just makes you understand how the drone variables in terms of what we're going to be estimating are located. So ux, u is a velocity, x is a position of that velocity, w is another velocity in a downward, up and down fashion, and z is obviously the position. Q is the pitch rate, so how quickly it turns, and theta is just the attitude at which the rate got it to. So one is the integral of the other. Hopefully everybody understands that, but if you don't, we will obviously, you will see the example. I mean, it will be quite obvious. Okay, so just again, just to get an understanding of how you calculate drag. So the resisting forces needs to be calculated, as I said. And here the drag force is defined, and most of you should know this, especially the aeronautical students should have a very good idea. The only thing that's quite interesting here, which is quite important, is that this drone specifically has got a frontal area or a side area, and it's got a frontal area. So this is what this A front and A side means. But because we calculate in drag, and the drone is able to move not just up and down, but left, front and back, the drag, the equivalent drag areas changes depending on its attitude, depending on its pitch angle. And that's what this is. This basically says that the equivalent or the total frontal area due to that is facing this velocity is a combination of the front and the side. So it's a combination of this and this area, depending on whether it's moving up or it's moving front and back. It's pretty, I mean, it might take you, if you didn't get it, it just take a while to kind of understand it. Now, in terms of the drag moment, this is quite important because this is, even though in later 4th year master, it's defined slightly different, the concept is the same. There is a drag moment. And basically that drag moment is a function of how quickly you're turning. So basically, if you can think about it, a fan that turns on its axis, if you stop the power, will stop turning. And the reason why it stops turning, because there's a drag moment that keeps it, that prevents it from going any faster. So it slows it down. So the more, so it's a function of the, the rotation, the rate of rotation. And that's what this is. So obviously it has taken some fictitious value len, which we described earlier, which is the moment arm. The moment arm, and it has taken the rate of rotation q times by some drag coefficient. And different drone design, different quadcopters, different aircrafts will, this resisting moment will be completely different. It will be defined differently, but the concept is the same. Okay. All right. So what happens with this is now you're able to now do some calculation, or at least state the calculations. And what this how this happens is you're able to now use the state variables, and we will define it later. So it might seem a bit confusing, but the Q is the state vector. So basically it's a placeholder of all the variables that we've stated here, which there's 6 of them, 1, 2, 3, 4, 5, 6. So there's 6 variables, and each one means something. For example, Q1 means the up and down drag velocity, that is W. Q2 is the forward backward drag velocity, or velocity, to be fair, it's not really drag velocity, and that's U. And Q4 is the pitch angle like we described for the drag, and that's theta. And as you can imagine, you can see the same kind of equation, but obviously in a MATLAB format, and both, all of them. Now, the reason why this, you know, 1 and 2 is because, you know, you have a drag force as you're going up or down, and you have a drag force as you're going backward and forward. That's really what this is. Okay. Now, this is where it gets a bit interesting. So this is now, we've spoken about aerodynamics. Then we need to get into how does the drone actually get to fly? And that's got a lot to do with the flight controller. So the flight controller, or the autopilot, which is within the flight controller, acts in giving commands to the motors. So to produce, if you go up, to produce these two forces, you have to command via this box, the flight controller, as we spoke about it. You command the motors to produce a force via the propellers. Obviously, the propellers turn, the faster they turn, the more force they generate, and so forth. But then it's not arbitrary. So the flight controller in this case has 2 variables. One is the throttle, 2 is the pitch. I just call it a pitch controller. And what this does, as it says that the relationship between the commands and the forces it creates can be analyzed. Obviously, we're not going to analyze it here, but the only thing that's certain is the throttle changes the magnitude of the force. So how much force, so how much it spins, how fast it spins, and how much force is generated. And the pitch controller changes the ratio. So it means, you know, you're able to change how much of that magnitude is partitioned between the 2 motors. So if I turn the knob, you know, I can change the length of it. And what that does, it changes the moment about the center of gravity. And that creates this motion. So if it was just equal, it will obviously just rise in this fashion. If it's different, it will obviously rotate. And that's the commands you send via the flight controller. And that's what this is. So these forces that are generated, there is a power multiplier. This power multiplier is a fictitious value, but it represents something physical, which is the amount of throttle that I can generate is dependent on real components, like the size of the motor, the size of the propeller, how much voltage I have in my battery. It depends on a lot of factors, and this is incorporated into this G value. But what is clear here is that obviously you have the throttle command, dethrottle here, and then you have the pitch command, which changes the ratio between the forces, and those forces now create a moment. And that moment is about len, which is the moment arm, as I explained earlier. So that's what really brings about the commands which interacts with the aerodynamics. Okay, so now you see that there's a way of balancing what we will call equations of motions. Okay, so those of you who have done third or fourth year flight dynamics should have a pretty good idea of where we're going with this. Okay, so now I think hopefully it's quite understood. Now we've defined the 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 all the different forces of different moments, and also we've defined the environment, and now we're able to what we call do equations of motions, which is now differential equations that we will be solving iteratively, such that we're able to model the simulation. We're able to simulate the model. Okay, all right. Again, this is done in MATLAB, so you just need to fire up your MATLAB in order for you to be able to do this. Okay, so like I mentioned earlier, there's a state vector with all the state variables or the variables that describe the motion. That's what a state variable is. It's a descriptive parameter that describes the motion. U, W, like I said, this is U is backward and forward, W is up, down, Q is pitch rate. Theta is the integral of Q. X is the integral of, if you remember, position is, velocity times time. So it's an integral. That's what this means. And Z is the integral of W, meaning that, the faster you go, the more elevation you get. And it's just the integral with time. Okay. If you don't remember this, just go back to your statics and class, or dynamics, you should be able to kind of make sense of this. Okay, so what happens here is, okay, sorry about that. What happens here is now we are able to now get an understanding how, so now what we do is in MATLAB, you have to initialize it, but it doesn't really, you don't really have to, but it's a good practice to initialize the state vector. Then what we can do is now calculate what we call linear and rotational acceleration. So Newton's second law really, talks about F equals to ma. To work out A, you divide F by m, and that's what this is. So to get acceleration in both up and down, the backward and forward and up and down, you are what you're doing now is you're adding up all the forces minus the resisting, obviously. So all the forces minus the resisting, except in Z, which is your up down, you need to add gravity, because gravity is a constant that acts in the down position, irrespective of where you are. So obviously, unless you go really far up, like in space, then it's completely different. But then what happens here is, obviously, we know what these F's are. But this here is the way it changes now. Now, if I go back, there's a sine and cos, and Q4 is, if you probably don't remember, Q4 is 1, 2, 3, 4. It's the pitch angle. Okay, so there is a difference in forces depending on the pitch angle in that direction. What does that mean? It means that if I tilt my drone in this direction, because the forces are fixed onto the frame of the drone, if I change it, looks like we're going to have 10 minutes left. So what I'm going to do is, very simply, guys, I'm completely sorry about this. What I'm going to do is I'm going to resend a meeting invite to all of you in 5 minutes time, and then we will be able to continue this, if not straight after or slightly later. Yeah, apologies for that. Looks like I'm talking too much. But in any case, it's quite important for us to kind of delve into the specifics. So what I was saying is that if you rotate the drone, the forces vector is fixed to that body. So in terms of the up and down direction, it changes its magnitude, and that is the cause of that angle of rotation, and that's what that is. So as you tilt the drone, obviously to go forward, you obviously change its force or acceleration in a various direction. That's what that is. Now the rotational acceleration is quite interesting. So what that is due to the inertia. So you have a moment, and you have a resisting moment, like we spoke about, and the subtraction of that. So if it's 0, there is no rotation. But the inertia, what it does is just, it's a mass property. Again, same thing like Newton's second law, but in the rotational sense. Okay, right. Now that's defined, what we can do is now set up some constraints. The constraints is quite important. What it does is just allows us to simulate things properly. And basically it just says Q6 is your velocity, no, your position, up down velocity. And basically it says if it's small, if it's very small and you have a downward acceleration, make that 0, meaning that it's on the ground, and that's a boundary. And similar to this is if you haven't cleared the ground up to a certain level, which is the half the distance of your drone, also make the rotation 0. Okay, all right. Now here's the interesting part. So what happens here is now we're able to take the rotational and linear acceleration and integrate them in order for us to get all the state variables. And that's all it is in terms of trying to understand how to get your velocities in your position. And this is quite interesting. You know, you should all remember V equals to U plus, or U equals to V plus AT. That's exactly what this is. You working out the velocities by just, is it's obviously a time step. The smaller the time step, the more continuous it becomes. But obviously the longer it takes. So what happens here is you're able to work out now all your velocities and your pitch rate, because we worked out pitch acceleration. Okay, so Q dot, you worked out pitch acceleration, you're able to work out pitch rate. And that's just an integral of that. Then you can do a second integral to work out positions or attitude, and that's exactly what this is. Now your pitch angle is now based on this value, and it's times the integral of a time step, and you can do the same with the position X and Z. All right, so what we're going to do now, hopefully this is quite interesting. For the next part, I'm going to stop it here. For the next part, I'm going to resend a link to all of you. Actually, I'm going to do it right now, and then we will go through the simulation. We will try and do some scenarios. If you only planned to, we will try and do it for the next 15, 20 minutes. It's not going to be that long, so it's still going to be the hour that you had planned. And we're going to do it right now. So let me stop this now, so at least you guys can